before we continue, I want to give you another sort of food for thought, for thinking at home. Just a problem about equivalence relations, similar to what we had I suggested a few weeks ago. So X is a set. It has two equivalence relations. With two different notations, so that one wiggle or double wiggle. Okay, so then we define a new relation in two ways. Triple wiggle. Okay, so there are two versions. A is X is equivalent to Y if X is equivalent to Y the first way, and X is equivalent to the other one the second way. Okay. Okay.
Thank you.
And now the same thing, but with OR. Okay, so prove or disprove that this is an equivalence relation. Okay. So that is a purely abstract problem. So we are trying to do a lot of abstract things, but not entirely. Not entirely. So, what for example, groups are abstract as they defined, but not the modular group. Modular arithmetic is not abstract; it's specific. Similarly, the equivalence relations that we have seen are the idea itself is abstract. Those three axioms. That's abstract definition. But the modular equivalence relations, modulo n, that's specific. A specific equivalence relation. Okay, so that's how we're doing it. We'll continue doing it for some time. So where the abstraction comes from, it is well, it's hard to explain how it happens, but it goes through several stages, and I think there is kind of explanation that you go from concept to generalization to abstraction. You ever heard this sequence of developments of ideas? Whether it's especially in mathematics, it's explicit, but also in other areas or other sciences. It is so you go from idea that not a concept that is there is no concept yet. It is something specific phenomenon or idea that you're looking at, and then you can see it is very specific, and then you might generalize it. You might generalize it in different ways, and you might see other examples of a similar idea, and then so that's the first stage. And you'll look at them and apply the same idea as the original, only in a more general setting, and then you see the similarities. It's like going from numbers to, say, vectors. Okay, so Rn, you have vectors, and you have they behave very much like numbers, and so that's the generalization. But then when you see enough examples of that similarity in a very different areas, then you come up with an abstraction. Which includes all of those examples that you have seen, as well as hopefully then the things that you haven't seen, and they are all that bigger idea that you come up with incorporates all of them. Okay, and so in the future you see something else, and then you just find it's like on your shelf there's a place to put it, and you know, okay, that's a group, that's a topology, that's something else. Okay, so anyway, in the equivalence relation, that's an example. Okay, so this is what we are doing. Proving axioms for the operation, this operation on on Z sub n. Okay, so addition, how do we add two equivalence classes? We simply add their generators. Turns out it doesn't matter which generators you pick. Generators, yeah, I think it is a fair way to put it. I'll call x is here. X is it is an element actually, simply put, of the equivalence class of x. Okay, so but there are many elements of that class. So if you specifically point out one, you can say it is a generator of that equivalence class. So that's how we define addition, and now we are deriving the axioms for Zn from the axioms, the same axioms for Z. So we assume that we know everything there is to know about Z, how we do addition there, and these are the four axioms on the right. So, and then we'll just moving on to Zn, and so turns out it's really uncomplicated. The actual, but it is interesting to the question number 3 or axiom 3 is to point out who serves as the 0 in this new group, and turns out it is the equivalence class of 0, very predictably. But it is interesting to see what equivalence class of 0 is. It is all the numbers divisible by n. So in other words, if you think about once again equivalence classes, so what happens is, where is that my picture of mine? What happened? Where's my picture? Here's my picture. Okay, so Z is written row by row, so it's kind of infinitely many elements put in a here 7 columns. Okay, 7 columns for n equal to 7, and as you can see, that the leftmost column is our 0. So all numbers divisible by 7 are in the first column, and that is the 0. So you can think about it as if what's happening is we are sets. We are now thinking of these sets not as sets anymore, but rather elements of some exotic group or exotic set. So the set of sets. So if you find that hard to manage, then you think of each of those sets as if it collapses to one point. So you can think of once again so all the numbers from the first column collapses to this one element of Zn, Z7, and that is the 0, one single element. And the same with every one of them. As you can see, the algebra works out whichever way you define it. But it is interesting that they are collapsing according to the same, pretty much the same plan. So there go. You push them towards that line in the middle, which points out the specific equivalence classes. Rather, it's not that they're specific. The generators are specific. So we choose, as you can see here, we chose the generators of those classes to be the remainders. So numbers between 0 and 7 and 6. Sorry. Okay. So once we identified what the 0 is, and we realized that everything is predictable, and so for example, part 4, once again for every so the writing is this. The statement of the theorem is the same, except we are replacing the statement of the axiom is the same, except we are replacing Z with Zn. So I take that statement on the right, and once again I say for every x in Z sub n. Okay, so I'm not using those brackets anymore. There is a minus x in Zn, whatever that is, and then once again, predictably, you can guess what that thing is. I here have to have 2 negative x plus x equal to 0, and here 2. Okay, so you can predict what that element is. Negative x is simply the equivalence class generated by negative x. Okay, so it's like all the algebra of Z that is taken, and then you put brackets everywhere. Okay, if you look at that That's exactly what happened over there. X plus y is equal to x plus y. Okay, so let's put brackets there, and then we have our the definition of our operation on Zn. Okay, so same thing happens with the axioms, with the 1 and 2 axioms 1, 2. I mean, if you just go, you try to write what that means. Well, probably. Well, let's write it separately. So so x. Okay, so what I'm talking about is x plus. I'm looking at the axiom 1. Okay, and I'm trying to write this in terms of my definition. So equivalence classes. So this time I cannot avoid. Well, I can't avoid it anyway, but avoid the actual reference to the equivalence classes. Well, so let's do it. Y plus z. So associativity, and okay. So how do I work my way towards towards what? Towards this. X plus y plus z, and the answer is you use the definition of the operation right there, and then somewhere in the middle we're going to be using the axiom for z. Okay, so well, let me write out this is the definition of the equivalence relation, of the addition of the equivalence relation. So it will be x plus, and this, what is this? This is y plus z. As simple as that. Okay, and on the right what I have, so this is the still questionable, I'm trying to prove it, and then I have x plus y plus z. Okay, so then what I do is I remove those parentheses. I don't need them anymore. I remove these, and then carry out addition. So once again, I'm looking at the definition of the operation. Okay, this is my definition. Okay, and so I'm rewriting it as x plus y plus z equivalence class, and same thing here, x plus y plus z equivalence class. Okay, so well, let's put parentheses where they belong, like this. Okay, and now now what happens is these two equaled by axiom 1 for z. Okay, so we're using definition twice. Well, actually, we're using 4 times. 1, 2, 3, and 4 on both sides, using the definition of the operation. And then at the end, we have one equivalence class on the left, one equivalence class on the right, generated on one hand, x plus y plus z on the left, and on the right, x plus y plus z. Okay, so, and then turns out it works out. So that's and then we have proven that the question marks that I put there works out. So this is axiom 1 for Zn. Commutativity is similar. Right, so the same idea. Just expand, and at the end you apply the corresponding axiom for Z. So that's what those arrows were meant to be. Okay, so the idea is that already there. Number 3, number 4, you can certainly in the same manner you can verify them. So let me do number 3, say. So number 1, number 3. So x 0 plus 0 plus x, right, is equal to, by definition, it is equal to 0 plus x. Then by axiom 1 for z, right, it will be x, and well, and then we're done. Okay, so that's how axiom 3 is proven. So so the standard is the same for all 4 axioms. You once again look you use the definition of the operation as many times as necessary, but somewhere in the middle or in the end you use the in the end more likely you use the corresponding axiom of for z. So this is number 3 for z. Okay. Any questions about this? Okay, so so that's what we got. So what then? Well, first of all, let's notice that this was fairly easy. Why was it easy? Because we knew that our computations were independent of the choice of x as a representative of the equivalence class of x. Okay, so it doesn't matter. So that theorem that preceded it, this one, the operation is independent of the choice of x, y. Okay, so as you can see, so if x and x prime are equivalent, y and y prime are equivalent, then you adding x to y, or x prime to y prime is the same thing. It will produce the right equivalence class. Okay, so that's why this was straightforward. We just keep referring to the operation, to that theorem, to confirm these things. Okay, so let's see. Okay. Okay, I see here another homework that I want to let you think about. So this one is about the Cartesian product. X and y are sets. Okay, and we know what x cross y is. Now, z is a set. Okay, and we are looking at two functions, f from x to z and g from y to z. Functions. Okay, and now I'm going to form a new function. I'm going to form a new set, x cross y. I'm sorry, I messed it up. The other way around. Z here, 2x and 2y. Okay, so two functions. And I'm going to form a new set, x cross y, the Cartesian product, and I'm going to form a new function, f cross y. F cross y, cross g is a new function from z to x cross y. A new function defined by f cross g of z is equal to f of z, g of z. Right, so this one is x and this is y, and so since we know output of z is the same, it's x, and output of g is also known. Once z is provided, I know f, and I know f of z, I know g of z. One of them is x, one of them is y. I combine together, and this thing indeed belongs to x cross y. Is this quite clear what this is? I wonder if you recognize the similarity with something that you saw in Calculus 3. So look at it. The input variable is the same. The output variables are different. I combine them together. What does it sound familiar? What if, especially I'm referring to this part. So suppose f and g are actually real-valued functions of real variables. So suppose x, y, and z are actually real numbers, and you have two functions of the same variable. You combine them together into one. What is that? Two functions of the same variable combined together. It is no. It's not a. It's not a cross product. I know. Not exactly. It is a product. A function into the product of two of x and y. So if x is real and y is real, then x cross y is what? R cross R. That's not the same as cross product that you saw in Calculus 3, which is about specifically limited to Calculus 2 to dimension 3 Euclidean spaces, multiplication of vectors. That's what cross product is. is in algebra and in calculus.
It's a plane.
It's a plane. Okay, so then we're talking about the function from my function here is from R to R2. What is it? A function from R to R2. What is it? In calculus 2? 3? I'm sorry. For each value, for each real value, the output is a vector in R2. What is this? How about I call it T? So I have f of t and g of t, and I put them together. What is it?
Is it like the parameterization thing?
Yeah, it's a parametric curve. Okay, so indeed, say the same input variable, which is t. Okay, which might be time, for example, but the output is different. And if you take those two outputs, combine them together, they will simply give you points on the plane, and then the result is indeed a parametric curve. So for each t, there will be a point on the plane, and together it is a curve. Okay, so that's an abstraction of that idea here. So as you can see, there is nothing. There are no r's here. There are no. There is no speaking of continuity or anything like that. There is no plane. It is an abstract set, three abstract sets, and x cross y is the not the cross product, the Cartesian product of x and y. So once again, an abstract operation on sets. So it simply produces all pairs of x and y. Taken together, they form this x cross y set. Okay, so then, but that certainly never forget when you face an abstraction. What do? It's hard, so you always go back and have a few examples handy that illustrate that abstract idea. So a parametric curve is a illustration of this situation. So cross product of not cross product, the Cartesian product of two sets. The best illustration or example or metaphor for it is there. R cross R gives you R2. So how you form the x-axis and the y-axis, take it together. You put them together as in the Cartesian product gives you the Cartesian plane. So once again, x's are Cartesian, and then you put them together appropriately. You have a Cartesian plane. Except in this environment, there are no distances, there are no angles, there is no algebra of any kind, so you don't add those vectors. It's a purely set theoretical thing. Okay, but it doesn't mean that there is nothing to talk about. And here's a question. So prove or disprove. A. Both f and g are onto, then f cross g is onto. And b, both f, g are 1 to 1, then f cross g is 1 to 1. Okay. So, well, you can think certainly once again frequently. One example will do the job, do the trick, and you can figure out the answers at least before trying to prove anything. Figure out what the right answer might be. So that example on the left might help. Okay. So so we have now a group. So Z is a group. Zn is a group. V sub n plus is a group. Okay, so just to refresh our memory, Zn either you can look at Zn two ways. Either Zn as the set, so set followed, comma, followed by the operation. So Zn is either equivalence classes of X, X and Z. Okay, so equivalence classes of modulo n, or congruence classes, mod n. Okay, so which is incidentally equal to just the list of classes 0, 1. There are only n classes. So if you want to pick the standard representation of those classes, this is how you do it. So even though you have infinitely many classes, infinitely many x's over there, but together they produce only n minus 1 equivalence classes. Okay, so that is the that's what we've got. We then the operation, just to we'll do it one more time. X equivalence class modulo congruence class of X plus congruence class of Y is defined to be the congruence class of X plus Y. Okay, so this is a group with two parts, a set and an operation. Okay, the only thing that I wanna well, you can tweak it a little bit, and you can alternatively write it like this, just to simplify things. Zn is simply the set of numbers from 1 to n minus 1. Okay, just like that. So not equivalence classes, you can just leave it alone and just pick the remainders. The remainders are then division by n, and there are n minus 1 of them, and so we don't have to deal with brackets. That will make our life easier. But then what is the operation? X plus y is equal to what is it equal to? And it is equal to x plus y mod n. Okay, so if x and y are between 0 and minus 1, when you add them together, certainly you can get number larger than or equal to n. Okay, but if you do it mod n, you're okay again. Okay, so that is more compact representation and kind of less structure there to worry about. You don't worry about sets, or the elements of my set are literally numbers from 1 to n minus 1, the n. Okay, and the operation, as you can see, you don't have to worry with brackets. You add numbers. You add numbers, but you add numbers modulo n. So that's also modulo arithmetic applies directly. So it's the same thing. So these two ways to interpret this group are equivalent, proving everything that this group also equivalent. The last one more compact, and so it's just usually it is the one that is used whenever you do anything with Zn. Okay. Okay, so I want to take a look at some examples, and I look at the structure. So the structure of Zn of, let's say, of a group. I wanna take a look at. Let's go to a simpler place when you can speak of structure of a group, and that is Z. So forget about all modulo for a moment, and then we have a bunch of groups. We'll have a bunch of groups with the same operation. So let me put them here. R, right? No, first Q, R. I could even put C here if I like. I could put here what is the so all are groups. So these are groups. Okay. What is so we're talking about what we call subgroups, and that is simply a group. That is simply a subset of a group which happens to be a group as well. Okay, so that's exactly what this example is supposed to indicate. So they're subsets of each other, and with the same operation, and they are also groups. Okay, so not only subsets, but they also take the operation from the larger group. So that's what they're called subgroups. So this, for example, you say Z is a subgroup of Q. And in turn, Q is a subgroup of R, and so on. And then certainly you can say, well, if I now take this, Q is a subgroup of R. Okay, so what about Z and R? Z is a subgroup of R, right? Which is, incidentally, this is called, an example of transitivity, right? Z is a subgroup of Q, Q is a subgroup of R, therefore Z is a subgroup of R. So it's a transitivity. Not the transitivity in the nature of equivalence relations. We're certainly not going to be speaking of equivalences here, but you can see that because it's one-sided. It is one-sided. You progress in one direction, you cannot reverse it. So that's why it's not an equivalence relation. It is more like an ordering. So that's another abstract thing that you can look into. It's ordering things. Ordering things of numbers, as we know, numbers are ordered. But there are other things to order, and that is, for example, you can order sets. You can order sets by inclusion. So you say that set A is bigger than B if A includes B, like that. And then you have an ordering. So that's another abstraction of a common concept. So anyway, what subgroups of Z do you know? We talked about that yesterday. The even numbers, that's right. So let me show you the notation that we frequently use. This, the even numbers. Oops. Okay, 2Z stands for even numbers. You see why? Why would we use this notation for the even numbers, 2Z?
Take any integer and multiply it by 2, then its product's divisible by 2, which makes it
Right, yes, and vice versa. Right, so indeed, you take all the integers, multiply all of them by 2, what are you going to end up with? All the even numbers, right? So that is, in fact, that little 2 there, it's like the indicating that bijection, remember, between Z and Zn. I'm sorry, between Z and even numbers. You multiply by 2 and you have all the even numbers. Okay, you can notice that the odd numbers aren't here. Okay, so then you can, similarly, you can think of, how about 3Z? Same story. These are numbers divisible by 3. So once again, take all the integers and multiply by 3, you have divisible by 3 numbers, and so on. Okay, so that's like a sequence of subgroups. It doesn't have to be a sequence. They could go like this. Not, they don't split, but well, you have already seen an example that it's like more like a tree than a sequence. So you can Z has many subgroups. Such as 2Z and 3Z and 5Z, and they're all here. Okay, so where is the n? How can we fit Zn into the picture? Is it a subgroup of anything here? No. Think about it. Well, first of all, we have two interpretations. The first one certainly doesn't fit because it's made of classes. So let's examine that idea. Is Zn a subgroup of Z? Okay. So this one cannot be the first interpretation. So we have 1 and 2. interpretations of our group, and the first one certainly doesn't fit because it's made of entities of a very different nature. They're made of inequality classes of integers rather than integers. So it's not simply not a subset. This is not a subset of Z. Okay, but this one is. This is a subset of Z. Okay, so so why is it not a subgroup? Because the operation is not the same. So once you put a mod n on it, it's not the same operation. So the idea of a subgroup in the sequences, it is clearly seen that the operation is exactly the same. I could take the operation on R and simply decide it. Let me apply to all the integers. The result will be the same. So it's the same, well, identical operation, and the difference between these groups is only in the domain of that operation. So what numbers are it's applicable to. But so that's why. So it's not here. That's why Zn is not a subgroup of any of these. Okay. So let's examine what Zn is. Does Zn have subgroups? That's what I would like to investigate. Okay, so I'm gonna go with n equal to 4, and okay. So then Zn is 1, 0, 1, 2, and 3, with addition mod x plus y is equal to x plus y mod n, mod 4. Okay. So when I wrote this, it's a little bit awkward to understand, I suppose. Here, this one is the operation of Zn, or Z4, while this one is simple addition. This is simple addition. So I'm explaining what, and we're using unfortunately the same symbol, but we sometimes it's just easier to keep in mind that there is something behind it that requires some extra thinking than to have a notation that is distracting. So we're using the same symbol. I put a different color so to indicate that, yeah, there is an issue there, not to be forgotten. Okay, so that's our operation. This is our set. Okay, all good. I say there is one very simple group, subgroup. 0. Is a subgroup. I mean, I probably should have brought it up way earlier, because this is the example of the simplest possible subgroup, which is contain exactly one element. And if you think about the 4 axioms, what is happening there? You add 0 to 0, you always have 0, and then there is nothing happening. So it is certainly a subgroup. So once again, what is the first axiom? 0 plus 0 plus 0 is equal to 0 plus 0 plus 0. 0 plus 0 is equal to 0 plus 0, so it's a abelian group as well. Is there a 0 in this group? Yes, it is. It is the 0. Okay, so 0 plus 0 is equal to 0 plus 0. Okay, 1, 2, 3. And number 4, what is negative 0? It's still 0, yes. Okay, so just make sure you go over these just to convince yourself. So 0 is a group to begin with. So it's worth just saying that it is the simplest group. 0 and the thing is that it is 0. Where is that? It doesn't matter, meaning that it is a subgroup of any group. So any group has a 0. Okay, if you form that a set made of that one element, it will be a subgroup. So it is a subgroup of any group. Okay, so once again, you have a group. The group has 0. If you create a set that consists of that single element, it will form a group. followed by this. This is the proof here, roughly. Okay, so ZN then at least has that subgroup. Are there more subgroups? Well, that becomes more complicated, but we could try to use our addition table. So I have 0, 1, 2, 3, 0, 1, 2, 3, okay, 2, 3, 1, 2, 3, 0, 2, 3, 0, 1, 3, 0, 1, 2. So that's my addition table of my group of Z4. Okay, so that's my all the additions are here. All the additions are here. The only thing now and then I'm supposed to create a subgroup. What is a subgroup if not it's also a group? So it has to have simply fewer. I have to say throw out one of the elements, and then or say one or more elements, and then remove the corresponding columns and rows, and then the result should be once again a table of addition of that group. Okay, as an example, paste. Okay, as an example, look at it. This is subgroup. This is my subgroup. If I choose 0, so I'm looking at the first column and the first row, and I have to decide which elements I pick from my my Z4. Which one? The number one example, I choose 0 and nothing else. Okay, then you see the table. This is the table of the 0 group, the addition table of the 0 group. Okay, so it works out because 0 plus 0 equal to 0, so we are okay. Okay, however, let me try to choose these. What if I choose these two elements? So the question I'm asking is this a subgroup? Is it? Zero and 1, it is a subset of our group of 4 elements, but is it a subgroup? You look at the operations, so both the first row and the first column represent the same group, so these are these elements. So then I extract my table. To answer the question, I look at the table of operations on this subset. So the elements are 0 and 1, and look what happens if I will be adding zeros to ones and zeros to 0, 1 to 1, 0 to 1. Right? And this is the table. So what's the answer? Is this a subgroup? No, because this 2. The problem with 2, it does not belong to this, let's call it G subgroup, hypothetical subgroup. Turns out that we added 2 elements within that subset, but they did not produce element of that subset. So it's not a subgroup. Okay. So well, let me try another one as quickly. So say I pick. How about this? If I enlarge it like this. So if I take 1, 2, and 3, I'm sorry, 0, 1, and 2. If I pick 0, 1, and 2, is it a subgroup? No. Once again, no, because we have these 3s, and so they're out. So does it mean that there are no subgroups? No, it doesn't mean that. So let me point out at one for which it does work, and that's 0 and 2. Remember, it works out pretty much the same way as when we discovered that even numbers form a subgroup of Z. Okay, so because even plus even is even. Okay, so what we tried originally, 0 and 1, even and odd, odd plus odd gives you even, and then you're in trouble. But this works out. So if we carefully try to extract the table, this is what happens. So once again, I picked 1 and 2. So this will be my G. 0 and 2, nothing else. So same thing here. This is my G. Okay, and now where is my table? And the table a little bit hard to find. Then this is whichever entries in my table that correspond to these 2 rows and 2 columns. I am to take. So this, and that. Okay, as you can see, when you add 0 to 2, you have 2. When you add 2 to 2 plus 2, you have 0, because it's mod 4. Okay, so that works out. And then to make clear that that's what we wanted to accomplish, I have 0, 2. I will create a new table for G. So table for G, 0, 2, 0, 2, and so 0, 2, 2, and 0. Okay, so that's my table. I just copy. I remove the elements that I don't need. In fact, well, probably okay. So this is. Let me just repeat the picture. So it is directly. This stuff is directly extracted from the original table by simply removing the table, the columns and rows that we don't care about. Okay, so once again, this is my G. Okay, now this is the crucial step of understanding of what's going on. What does it look like? This new table.
0 and 1.
That's right. In other words, what? 0 and 1, what do we call it?
Is it mod 2?
What?
Is it mod 2?
Yes, it is mod 2. It is Z2. Z2. It looks very much like the table of Z2. So let's Z2. Let's see what it looks like. 0, 1. 0, 1. The difference is only in the name. And we know that. We don't really care about that. So as you can see, there is that's a match. What that match means exactly needs to be clarified. But as you can see, with only renaming 2 as 1 is all that it takes to turn one into the other. Okay, but once we clarify what this match means, we can declare that we have found Z2 inside of Z4. Okay? All right. So I guess I'll see you after the break.